the addition of two graphs. So if I have to draw function x plus g of x, then what we do is draw each of them separately and then add the ordinates together. I think in science they call this superpositioning of graphs or something like that. All right, so let's do y equals x squared plus x. So a couple of simple ones there. So y equals x squared, there it is, our standard parabola. Y equals x is, of course, our straight line. Now, we're going to add these two graphs together. The first thing is x and y intercepts. I'm going to mark in the origin because that's an x-intercept. In fact, it's an x-intercept on both. So 0 plus 0 is 0. I know that's going to be an x-intercept. The other x-intercept I'd be looking for is over here on the left-hand side. I would tend to get my ruler and just slide it along. And whenever the measurement above is the same as the measurement below, then I know, okay, that's got to be 0 because one's positive, one's negative. That must be where the x-intercept is. So somewhere about there. Then it really is a matter of just, well, I say draw lines perpendicular here again, but it could be just a matter of you sliding your ruler along at different points. But for the sake of our example, I'll draw in. Now, point of intersection is always a good one, because if I'm adding those together, it'll be twice whatever that y value is. So I'll plot that there. And then, as I say, as many as you need. I might have gone a little bit overboard, but as many as you need to get a feel for what the shape's doing. And as I say, you just simply add, however many centimetres below, minus from how many centimetres above, and so on. Okay, so let's start plotting some points. Oh, look, there. And we see, okay, the shape then must be, something like that. That's really all there is to it. Let's try one where there's some asymptotes. So y equals x plus 1 on x. So there's y equals x and y equals 1 on x. Now, x-intercepts here is a little bit harder because, well, the x-intercept of the straight line is up when there's a discontinuity in the other one. Well, the discontinuity's got to remain. I can't add something to the undefined. So my new graph will also be undefined there. When is it the same above and below? Well, that's never going to happen with this graph because on the right-hand side it's always above and on the left-hand side it's always below. So I think I'll plot in the point of intersection and there's another one down there. And then I'm just going to continually add points, as I say, to get a feel for the shape. Now what we should be finding, imagine I'm adding the hyperbola to the straight line. As I go to the right, I'm going to be adding smaller and smaller amounts. So I should be getting closer and closer to the line y equals x. Kind of makes sense, because if we look at the equation, y equals x would be the asymptote. So yes, it is going to get closer and closer to that. So this particular one, there we go, we're inside the hyperbola line, that little section there. Keep in mind, as I mentioned, discontinuities. If you've got a discontinuity in the original function, that'll remain in the new function when we're adding them together. So yeah, x plus 1 on x we just did, but it would be the same for 1 minus 1 on x. Now, here's the interesting one. If I was to actually add those two together, add them together and it looks like we've got the line y equals x plus 1. But we have to remember, the original graph, we couldn't add in x equals 0. So it's a bit like that other one we saw the other day. You remember the x on x one? Be the same sort of thing. This one, I'd draw y equals x plus 1, but there'll be a point discontinuity at x equals 0. Because I'm not actually drawing the line y equals x plus 1. I'm drawing the line x plus 1 on x plus 1 minus 1 on x. And I can't substitute 0 into that because of the bottom of the fraction. X-intercepts, that's what I was talking about, the same above as below. So if one's positive, one's negative, they'll add together to give 0. Symmetry. Okay, functions will retain symmetry when they're added. So if you have a look at the one we got up there, x plus 1 on x, they were both odd functions. So when we added them together, we still ended up with an odd function. We still got the rotational symmetry. So an odd function plus an odd function will give you an odd function. An even function, if you're adding to it another even function, your answer should be an even function. Now if you add an odd with an even, it's not necessarily going to have symmetry now. This one. Absolute value of x plus 3 plus absolute value of 1 minus x. For these absolute value ones, I like to investigate at the critical points, same as if we were solving the equation. Now the critical points here are when each of these absolute values would equal 0. So -3 is going to be a key point and 1 is going to be a key point. So if I was on the left-hand side of -3, pick any number you like that's smaller than -3, anything you like. X plus 3, does it give you a positive number or a negative number? So therefore, if I'm finding the absolute value of that, that will be negative x plus 3. Remember our definition for absolute value. It's going to be positive when it's greater than 0, but it'll be negative when it's less than 0, because we need to turn it into a positive number. So therefore, with the x plus 3, we said x plus 3 would end up being a negative number, so the absolute value of that must be the minus of x plus 3 to turn it into a positive number. Now what about 1 minus x? Same number, whichever one you picked. 1 minus that number, positive or negative? Positive. So this one will stay as 1 minus x. So my new graph then, when I add that all together, I'll be drawing the line y equals minus 2x minus 2. Okay, now pick a number in between -3 and 1. I know what number I'm picking. X plus 3, positive or negative? Positive. So okay, that stays as x plus 3. 1 minus x, positive or negative? So it stays as positive. So in between, in between -3 and 1, we'll just be drawing the horizontal line y equals 4. Now I want you to pick a number bigger than 1. X plus 3, positive or negative? So it stays as x plus 3. 1 minus x, positive or negative? So it will be the negative of 1 minus x. Add them together and we'll draw 2x plus 2. So this particular graph, okay, the first part we said we're drawing the line minus 2x minus 2, but we stop at -3. Then we said we're going to draw y equals 4, but we stop over there at x equals 1. And then we're going to draw 2x plus 2. And so we get this, I don't know, what do you call that shape? I was going to say U, but it's not really a U. A cross-section of a bucket. There we go. So that's the shape we get for that particular graph. Now, if you had to draw function x minus g of x instead, personally what I'd do is I'd draw function x, but then I'd draw negative g of x. So flip it, and then I'm still just adding the two graphs together. Still the same idea. So here we go. Let's have a look at this one. Y equals x plus g of x, where g of x is bounded. Now, g of x in this case is sine x, or rather, minus sine x, because I'm doing the negative. It's bounded. So what I mean by that is its y values are always in between 1 and minus 1. It doesn't go anywhere else. Now, what will happen when we draw this is our new graph will be bounded by x plus 1 and x minus 1. Those two lines. Let's see what happens. Let's plot some points. So when I add 0, so when sine 0, add it to the red line, I'm at these points, and unfortunately with my scale I can only get 3 of them in, the others would be up the top and so on. The other points that are good to draw on something like this are all those turning points. So when they are 1 and when they are minus 1. And so you should find, well, I've only got 1 point drawn, but if I was to draw more, this one should lie on y equals x plus 1, the boundary that way. And this one underneath should be on the line y equals x minus 1, the other new boundary. It would end up winding around the line y equals x. But notice the symmetry of it. It's not perfect like the sine curve. See how that turning point is closer to the origin than it is to the next intercept? So it's sort of been a bit distorted as it goes up on that one. Alright, so that's adding and subtracting. If I want to multiply two functions together, similar idea. I'll draw the two construction graphs first of all, so function x and g and x. And then, okay, I'm going to draw in here x e to the power of x. So y equals x and y equals e to the power of x. So there's y equals x and there's my exponential e to the power of x. X-intercepts, they're going to be important because that's when it will change from positive to negative. We talked about that the other day with change of sign. Key points. So the only x-intercept here is when y equals x. So that one I'm interested in. So basically we mark in all the x-intercepts. In this case I've only got one. Okay. Then you have a look at each function and work out whether it's going to be positive or negative. So on the left-hand side, I don't know what the values are on where y equals e to the x, but I know they're going to be positive numbers. And for y equals x, I know it's negative numbers. And if you multiply a positive with a negative, you get a... Therefore, I know the curve's down there. Now when I go past that x-intercept, the exponential is positive, y equals x is positive as well. Positive times a positive gives you... Therefore, I must be in that section there. So I know where the graph's going to exist. Y-intercept, well, we've already marked it for this one because it turned out to be the origin. But you can always work that one out. 1 or minus 1. Because if I'm multiplying by 1, the number stays the same. So wherever 1 is, well, I haven't put a scale here, but let's say that's 1, then I know I'm multiplying the exponential by 1, so it'll stay in the same spot. So let's assume it's there. So then the exponential would go there. See what I'm saying? So at that point there, that's when on the y equals x, y is equal to 1. So therefore, when I multiply the exponential times that graph, I must end up on the exponential. Similarly with negative 1. When y equals x is negative 1, well, this time it won't go on the exponential because I'm multiplying by a negative amount. But it'll go the same distance below the x-axis as it was above the x-axis. Okay. Function x of gx approaches 0 or infinity, then so will the new function. So looking at this, right-hand side, let's look at that one first of all because that's probably easier. The right-hand side, our exponential is going off to infinity. So is y equals x. So if we multiply them together, yeah, it's a pretty fair bet they're going to infinity. Now on the left-hand side, the exponential is going towards 0, but y equals x is going towards minus infinity. And we're going to multiply those together. Infinity times 0. What do you think we get? Anyone want to guess without cheating and looking? You sure? And I'll have a look at the sheet here. Right. In this situation, you go for the curve that dominates. Now, how do you tell which one dominates? You're looking at the curve that gets steeper or shallower the quickest. So out of the exponential and the straight line, which one gets steeper or shallower the quickest? So it will behave like the exponential. So this one will go towards 0. We end up with something like that. Right? So it ends up going asymptotic to the x-axis. It's going to go towards 0. Things to keep in mind. Discontinuities, just like the adding, if they exist in the original one, it's going to exist in the new one. Symmetry, some type of symmetry will remain. Right? Odd times an odd will give you, no, it's even. Odd function times an odd function gives you an even function. Even times an even gives you, that also gives you an even. Odd times an even, odd. So basically if it's the same type of symmetry, they'll multiply together to give an even function. If they're different types of symmetry, they'll multiply together to give an odd. All right, let's have a look at this one. And I've already drawn in the 3 bits that multiply together. So we've got y equals x squared, my parabola there. X plus 1, the straight line. X minus 1 cubed, the cubic. Now, we've seen ones like this before, so we have that way of doing it. This is just another way of thinking about how we could possibly draw this. So if I do it by the way I just went through, first thing, x-intercepts. Let's mark them in. There's one at negative 1, 0, and positive 1. That will break my graph up into boundaries. On the left-hand side, starting out here, the red graph is positive. The blue graph is negative. The whatever the colour that is. We reckon pink, purple. As I say, whatever colour it is, it's negative. Positive times negative times negative, positive. So we know we're there. All right. In between the next 2 intercepts, positive times negative. Now between the next 2, positive times negative, and there. Now the last section, positive times positive. So we now know where it exists. Gosh, can you see it there? It's in green, but it's sort of been hidden by the shading. Hang on, let's get rid of that. There we go. It looks like I've gone really flat here, but that's because of the scale I'm using. It actually comes down to a turning point, which happens to be very, very small for this graph. But that's how it turns and then comes back up to the 1. Okay, what about if I just square a graph then? So multiply it by itself. Multiply by itself. Any single roots will become double roots. Here's our random graph from before. Okay, any single roots, so we've got single roots, well, we've got 3 of them. They're going to become double roots. There, and there. Now what's significant about that? Double roots are turning points. So we know it's going to come down a touch at those x-intercepts. Stationary points will still be stationary points. The y value might change, but at those x values. So up here, that's a turning point. At that x value, it'll still be a turning point. Well, what's going to happen to its y value? This number is bigger than 1. Square a number bigger than 1, and it is bigger. So it should go higher up there somewhere. -1, well, you'll notice I changed the scale on this one, so it's a long way below that turning point. If I square a number smaller than 1, the number becomes smaller. But in this case, it's going to become positive, so it's flipped to the other side. So I've got to go through those. Now, discontinuities remain. Horizontal and oblique asymptotes might change because you've got to square the value of the asymptote. So in this case, my vertical asymptote, that's going to stay there. My horizontal, again, I don't know what that number is, but I do know it's smaller than 1. What did we say? Square a number smaller than 1. So therefore, that horizontal asymptote should be lower. It's going to become smaller. All right, so we've got points that we have to go through. Is that enough information? Okay, listen to this one carefully. If, and I'm just talking about the magnitude, not about plus or minus, but if the original graph is bigger than 1, then the new curve, the one I'm squaring, is going above the old curve. Because its y value will be bigger. If it's less than 1, then my new curve will be below my old curve. So, 1 is a key point. Let's plot that in. When we square 1, we get 1. Now, if I start at the left, my curve is below 1. Therefore, my new curve should be below the old curve. Then I'll go through this dot at 1, but now my new curve will go above the old curve. I'll plot in, it was -1 here, that's now going to become +1, so that one's flipped. Voila! So if you have a look at it, it's going from below 1 to above, and so on, and so on. Let's get rid of the old graph too. Yeah, a lovely little graph. We did addition, we did subtraction, we did multiplication. Let's complete the set. And we'll do division. Division really is multiplication. You're just multiplying by the reciprocal. So a lot of the ideas are the same. But now x-intercepts will become vertical asymptotes for g of x, because we're turning into a reciprocal graph. And when we did those reciprocal graphs, we said x-intercepts become vertical asymptotes. So here's x plus 1, x minus 2 over x plus 2, x minus 1. Drawn in the 4 lines, we will have x-intercepts at -1 and 2, because that's the top of the fraction. But the bottom of the fraction, we won't end up with x-intercepts, we'll end up with asymptotes. Now I can work out my regions, because I can still use the same idea. Negative times negative times negative times negative gives me a positive. Positive times negative times negative times negative gives me a negative. Positive times positive times negative gives me a positive. Then we've got positive times positive times positive times negative gives me negative. And finally, positive times positive times positive times positive, positive. So I know I'm in all of those sections. Y-intercept, sub in 0, we get 1. So we know it's there. Investigate the behaviour. Are there any horizontal asymptotes, oblique asymptotes? That idea of dominance that I talked about before. Well, do a polynomial division, and that's what we get. So therefore I know there's a horizontal asymptote at 1. Let's draw that in. I've got to go through those points. I've got to bend towards the asymptotes. I've got to be in the sections that I've shaded. Hopefully that's enough info. Let's draw it in. Voila. Oop, get rid of the shading so you can see it. There's a lot happening there. So it's that, that dark bluey line that we're looking at there. I'll show you this one. This is interesting. So y equals sine x divided by x. So I'm going to divide sine x by x. There's y equals x. There's y equals sine x. Okay. X on the bottom. Well, all the other x-intercepts, so the sine x, they will become x-intercepts because I'm multiplying by 0. At x equals 0, though, there's a discontinuity. It's not a vertical asymptote this time. Turns out that the limit as x approaches 0 of sine x on x is actually 1. Now you can try that by subbing in a very small number into sine x on x. Be careful though, your calculator has to be in radians for this, and you should get a value very close to 1. It's what's known as the small angle theorem. For very small angles, the sine of the angle is the same as the angle itself. So at 1, I end up with a point discontinuity. So it's still a discontinuity, it's just not an asymptote. Okay, what else do we notice? Well, I can shade in the areas. That's where this curve is going to exist. So we're getting y equals sine x, and we're going to divide by bigger and bigger and bigger numbers. We're dividing by x. Divide by bigger and bigger numbers, what happens to your number? Gets smaller and smaller and smaller. So this curve, it still looks like a sine curve, but as it winds down, it's actually getting closer and closer to the x-axis. It's also an even function because sine x turns out to be an odd function. Y equals x is an odd function. Odd divided by odd is even. Oh, I think that'll do us.